Hey students, today we're going to be using your knowledge of molarity and stoichiometry and combining those together to complete some practice problems. Number 1 asks how many moles of solute are present in 250 milliliters of a 0.5 molar, remember this capital M means molar, solution of copper 2 sulfate. So what do we need to do here? We need to figure out how many moles are in that 250 milliliters if it's at that concentration of 0.5 molar. Now, we know that molarity stands of moles of solute per liter of solution. And so let me write that here. We know that 0.5 molar is the same as saying that we have 0.5 moles of solute, which is the copper 2 sulfate, per 1 liter of solution. Now what we can do with this is use it like a conversion factor. So we know that the ratio is 0.5 moles to 1 liter. Also, we can write down here, instead of 1 liter, we can also write this as 1,000 milliliters. So those are interchangeable. 1 liter is equal to 1,000 milliliters. In this case, we're working with milliliters. So we need to convert from volume here, 250 decimal milliliters of this 0.5 molar solution, and we're going to convert the volume of this to moles of this to find out how many moles are in it by using this as a conversion factor. I want milliliters on the bottom of the solution, so I'll put solution here on the bottom so that that'll cancel. Milliliters of solution on top, milliliters of solution on bottom. I know that the molarity is per 1,000 milliliters, as I said over here, and I know that there are 0.50 for sig figs moles of CuSO4 per 1,000 milliliters. So now if we do this calculation, just like we do any dimensional analysis problem, we would multiply the 250 times the 0.5 and divide it by 1,000 milliliters. And we're going to end up getting, and also our milliliters of solution will cancel here. We're left with moles of copper sulfate, which is what we want. And so we would end up getting 0.13 moles of copper 2 sulfate. So we're simply using the molarity as a conversion factor. Now just real quick, if you were given an amount of moles and you wanted to figure out how much volume there was, you could also flip this over to go from moles to volume if you needed to do it that way. But that's not the problem here. Now, in the next problem, it's saying what mass of the solute in grams is present in the solution from above. Well, we already figured out how many moles there were, and so we're just doing a simple one-step conversion. If I have 0.13 moles of copper sulfate, all right, I can use the conversion factor, the molar mass. I know that 1 mole of the copper sulfate will equal the molar mass, which is 159.61 grams. 159.61 grams of CuSO4. Again, let's check our units. Our moles of copper sulfate will cancel, and when we multiply that out, we're going to get about 21 grams of the copper sulfate. Okay, so this is, number 2 is not anything new. It's what we've already done. Number 1 is the real new step here, where we're using the molarity to find out how many moles we have in that volume of solution. All right, number 3 asks us if a student reacts 100 milliliters of a 1 molar solution of acetic acid with 5 grams of sodium bicarbonate. And then we've got some questions on that. What's the limiting reactant is A, and then if we scroll down, B, how much carbon dioxide would theoretically be produced in grams. The first thing we need to do here is get a balanced reaction. So take a second and come up with the balanced reaction. Here's what you should have gotten for your balanced reaction. We have our sodium bicarbonate sodium bicarbonate here reacts with the acetic acid to form sodium acetate, carbon dioxide gas, and water. Now, if we balance this up, all of the mole ratios are 1 to 1 to 1 to 1. So we don't need to write anything in there. Now, how much of each thing do we have? I have 100 milliliters of a 1 molar solution of acetic acid, and that's this reactant here. So I have 100 milliliters of 1 molar I'm leaving out my decimals, but for sig figs that matters. And then we have 5 grams of the sodium bicarbonate, because that's a solid, that makes sense. Acetic acid is a solution, and so molarity makes more sense to use with a solution, and grams makes more sense to use when we're measuring a solid substance. So also paying attention that this is saying that we're at STP for now, and that's going to come into play later. The first question is asking, what's our limiting reactant? So just like we've always figured limiting reactants, we need to pick a product, and since later we're going to need to know about CO2, we're going to go ahead and go to CO2. We're going to take the amount of acetic acid, and we're going to do stoichiometry to get to moles of CO2, and we're going to do the same thing with the 5 grams of sodium bicarbonate and go to CO2. Whichever makes the least amount of CO2 is going to be our limiting reactant. So let's work this out, and we'll go ahead and start with the 100 milliliters of 1 molar sodium acetic acid. Again, here we have a volume and a certain concentration of acetic acid, and so if we start with that volume, 100 milliliters, we can use the molarity as a conversion factor to find out how many moles we have. So I know that it's a 1 molar solution, which means that there will be 1 mole of the substance HC2H3O2 per 1,000 milliliters. And I simply put 1,000 milliliters here because I'm in milliliters here. I could easily convert this to liters and use 1 liter down here, but it's easier just to put it down as 1,000 there. Now, that takes me to moles. Now I can use the mole ratio to go from moles of this to moles of CO2. And I know it's a 1-to-1 ratio. So I know 1 mole of the acetic acid will produce 1 mole of CO2. Okay, so it's as simple as that. We are taking the volume, converting it to moles, using the molarity as a conversion factor, and then using the mole ratio to get to one of the products. And we chose carbon dioxide since we're going to need to do more with that later. Whenever we put this in, we'll punch that in just a second. We're going to do the same thing here. We're going to put the 5 grams of the sodium bicarbonate. I'm just going to put SB for that so we can move through this a little quicker. Now, how do I go from grams to moles? I need to get to moles so I can use the mole ratio. And here we're going to use the molar mass, which is about 84.00 grams of the sodium bicarbonate is equal to 1 mole of the sodium bicarbonate. And then we need to use the mole ratio to get to CO2, just like we did up here, so we can compare those. And it's 1 mole of sodium bicarbonate will produce 1 mole of CO2. So let's calculate those out real quick and see what we come up with. All right, so what we found out is that from our acetic acid here, we will produce about 0.100 moles of carbon dioxide, and I'm paying attention to the 3 sig figs of the molarity there. And from the sodium bicarbonate here, we would only produce 0.0595 moles of carbon dioxide. So which one's the limiting reactant? The one that makes the least amount of product. That makes the sodium bicarbonate our limiting reactant. Okay, so the 5 grams of sodium bicarbonate is what limits us to the least amount of product here. All right, let's keep going. How much CO2 would theoretically be produced in grams? Well, if we already went to moles of CO2 up here, all we have to do is convert that to grams. So we know the limiting reactant will produce 0.0595 moles of CO2. And we'll just go ahead and do a quick one-step conversion to go from 1 mole of CO2, so the units cancel, and to get to grams, we're going to need to use the molar mass. And the molar mass of carbon dioxide is 44.01 grams of CO2. When we punch that in, we are going to get 2.62 grams of CO2. Okay, so again, we are really doing stuff that you guys have already done multiple times in previous units. The only new thing is incorporating this, taking a volume and using the molarity to get to moles, so we can use that in the stoichiometry. All right, so that's our answer for B. Now it's asking us, all right, now we're going to say we're not at STP anymore. What volume in liters of CO2 gas would be theoretically present if the reaction took place at a temperature of 17 degrees Celsius and a pressure of 720 torr? Now if we think about this, we have a gas. It's not at STP, so we can't use 22.4 liters. We're looking for the volume of gas, and we have a temperature, and we have a pressure, and from the previous problem we also know how many moles we have. So we can use the ideal gas law, the ideal gas equation, PV equals nRT. Let's list out the things that we have. We know that the pressure here of the gas is 720 torr. We know that the temperature of the gas is 17.0 degrees Celsius. Your brain should automatically go, oh, it's in Celsius, and I'm going to plug it into an equation. I have to add 273. So I'm going to write that down so we don't forget to add 273. What does that give us? 273 plus 7 is 280 plus 10 is 90. So we're in 290 degrees Kelvin. Got to be in Kelvin, all right. All right, what about volume is what we're looking for. So we're going to solve for volume. We already have the amount of moles of carbon dioxide because we calculated that up here. So, and we have it here as well, 0.0595 moles. 0.0595 moles. And the last part of the equation is our R value. Now we need to think about what are our units here. Our units are in torr, and we're going to need an R value that matches torr. Well, torr and millimeters of mercury are actually the same measurements. And so if we look at our units for millimeters of mercury, the R value is 62.4. So we're going to use 62.4 for our R value, 62.4. Okay. Now let's go ahead and rearrange our equation. In order to solve for volume up here, we're going to need divide by pressure. So the volume of the gas is going to be equal to moles times the R constant times T divided by P. And we just need to plug all this in. So go ahead and plug all that in and see what you come up with. So I have all this plugged in. I have my moles, I have my 290 Kelvin and my R value. And then I have my pressure units on the volume here. And again, I like to cancel these out. So we have moles on top here and bottom. We have Kelvin on top and bottom. We have torr that we can cancel. And look, we're left with liters, which is exactly, we're solving for volume and we're left with liters, which is a good thing. Whenever we plug all this stuff in, we're going to get that the volume of the CO2 gas at those conditions will take up a volume of 1.50 liters of CO2. Okay. Again, that's something you already know how to do, and so we're just practicing some of the skills that we've already done in the past. All right, let's go to our last practice problem. Here we have a student mixes 500 milliliters of a 0.05 molar solution of potassium iodide with 500 milliliters of a 0.1 molar solution of lead 2 nitrate. What is the theoretical yield of the precipitate in grams? Now, we have two different solutions we're mixing together. This is a double replacement reaction, and we're going to end up with a solid precipitate, and it's asking how much is going to be produced. Since we're given the amounts of both reactants here, we're going to have this is a limiting reactant problem. We're going to have to figure out which one is the limiting reactant, just like we did in the previous problem, and then we're going to figure out how many grams of the precipitate would form. Before we can do anything, we need a balanced reaction. So take a second and write out the balanced equation. This is what your balanced reaction should look like for our mole ratios that we're going to use in just a minute. Now, it's really important for this problem that we know which product is actually going to form a precipitate. So how do we know that in a double replacement reaction? Well, remember we start with two aqueous or dissolved solutions here. We're going to end up with one solid and one solution. How do we know? We need to go look at the solubility chart. If we look at the solubility chart that's in your course pack, you would see that potassium and nitrate are soluble with just about everything. And so this is going to form an aqueous solution. But lead is insoluble with a lot of things, and it's definitely not soluble with iodine. It forms a bright yellow precipitate after the reaction happens. All right, so now we have our balanced reaction. We know the precipitate is the lead-2 iodide, and we need to figure out how much lead-2 iodide we're going to form. So we need to take both of the amounts here and here and take both of those to grams of the lead-2 iodide. And why am I going to grams here? Because it's asking me for the product in grams, so I might as well just take them both to that amount. Now, let's set this up. For the potassium iodide, I have 500 milliliters of a 0.05 molar solution. So I'm going to start with the 500 milliliters. That's my known here. And I also know the concentration is 0.05 moles per 1,000 milliliters of solution, or 1 liter, same thing. So I'm going to put 1,000 milliliters on the bottom and the 0.0500 moles of Ki, potassium iodide, on the top. Again, this is all we're doing here is taking this volume, the 500 milliliters, at the particular concentration and using that as a conversion factor to find out how many moles of potassium iodide are dissolved in that 500 milliliters of solution. But we can't stop there. We need to go ahead and use the mole ratio, and here it tells us it's a 2-to-1 ratio, 2-to-1. So 2 moles of Ki will produce 1 mole of PbI2. And like I said, we need to get to grams here, so let's just go ahead and take both of these problems all the way to grams. So we need to go we know 1 mole of PbI2 has a mass of 461.01 mole, grams. Let me try that again. Grams of PbI2. Okay, so when we calculate that out, we're going to get 5.76 grams. 5.76 grams of PbI2 will be produced from the volume and concentration of potassium iodide that we started with. Now we need to do the same thing with the lead-2 nitrate. And we have 500 milliliters of that as well. 500 milliliters of the solution from up here in the problem. But this solution is a 0.1 molar. And so we're going to say, I know that that means that there is 0.1 moles of our solute, the lead-2 nitrate, in 1 liter of solution, or in this case, since we're in milliliters, 1,000 milliliters of solution. Okay. That'll take us to moles. Now we can use the mole ratio and figure out how much lead iodide there is. And now it's a 1-to-1 ratio here. So 1 mole to 1 mole. I'm being a little lazy with my units, but you guys know you should label your units in there and make sure they cancel out. Again, the last step is going to be the same step we did here. In order to get to grams of the lead iodide, we're going to go ahead and say 1 mole of the PbI2 will produce, will have a molar mass of 461.01 grams of PbI2. And when we plug that in, when we multiply that out, we get about 23.1 grams of PbI2. Okay, back to the question. Which one is actually going to be produced? The potassium iodide only produced 5.7 grams. The lead nitrate produced way more. There's no way we can produce this amount. It's too much. We don't have enough of the potassium iodide to produce that. So in fact, our limiting reactant is going to be the potassium iodide, and that's how we know what the theoretical yield of the product is. It's from the limiting reactant. So we're going to produce 5.67 grams of lead iodide. That's how you work some of these problems. I'd recommend, if you're struggling with these at all, keep practicing on using that molarity as a conversion between volume to moles, or in some cases you might have moles and need to get to volume, but continue to practice that. Thanks for watching. Have a great day.